This paper, titled Spacetime as a Dynamic Ocean, a modulation-based framework for gravitational field emergence, authored by Christopher Young, proposes a novel theoretical framework that reconceptualizes spacetime not as a static geometric backdrop, but as a dynamic oscillatory medium. The analogy used is that of a vast ocean with complex wave patterns, pressure gradients, and resonant structures. The primary purpose is to develop a mathematically rigorous model in which gravitational phenomena emerge naturally from pressure gradients within this modulated spacetime field, rather than from mass-curving geometry as in general relativity. Additionally, the framework introduces an auxiliary modulation coordinate, or AMC, which couples to conventional space and time and provides a deterministic underpinning for quantum effects traditionally treated probabilistically. The paper aims to unify gravitational and quantum phenomena under a common mathematical structure and to offer precise predictions consistent with observed gravitational measurements. The introduction sets the stage by revisiting fundamental questions about the nature of spacetime. While Einstein's general relativity treats spacetime as a smooth, curved manifold shaped by mass and energy, several foundational puzzles remain. What intrinsic properties give spacetime its elasticity? How does spacetime respond to energy and momentum? And crucially, how can the smooth geometry of spacetime be reconciled with the discrete, probabilistic nature of quantum mechanics? Rather than viewing spacetime as a passive geometric entity, this paper proposes viewing it as an actively modulated field, an oscillatory medium with intrinsic pressure patterns and harmonic resonances. In this view, planetary bodies and other mass-energy systems inject modulation patterns into the spacetime ocean through their rotational and internal dynamics. These modulations create pressure gradients that manifest as gravitational attraction. The key insight is that gravity emerges not from curvature, but from dynamic modulation and resonance within this oceanic spacetime medium. Moving beyond metaphor, the paper carefully distinguishes this ocean analogy from classical fluid mechanics. The spacetime ocean is a continuous field, not composed of discrete particles or molecules, and its properties emerge from modulation patterns rather than constituent elements. This shift reframes the fundamental question from how does spacetime curve to how does the spacetime field modulate. The framework emphasizes oscillatory patterns, harmonic layering across scales, from quantum to cosmic, and deterministic attractor dynamics that explain quantum phenomena as stable, coherent configurations within the modulation field. The mathematical foundations begin with defining the spacetime modulation field, denoted as phi spacetime x t eka. This field depends on three coordinates: spatial position x, local time t, and an auxiliary modulation coordinate e, the AMC. The AMC extends beyond conventional spacetime dimensions and enables deterministic modeling of quantum behaviors. The modulation field is expressed as an integral over sinusoidal terms representing fundamental oscillations with amplitude a, spatial wavelengths lego e, temporal periods ti, and a sum over orthogonal spatial modulation modes n. An entropy or coherence function sxt acts as a filter, suppressing configurations that are not harmonically stable, thereby selecting resonant patterns that persist. This formulation captures the layered harmonic structure of the spacetime ocean and explains why physical laws appear consistent despite underlying complexity. Complementing the spatial modulation is a temporal modulation field, TF, which models time itself as a complex oscillate structure with multiple components. These include quantum oscillations linked to phase evolution, resonance terms coupling to the AMC dimension, temporal decay envelopes stabilizing the field, nonlinear collapse thresholds, and quantum stabilization terms. An entropy-resolved resonance filter ensures that only harmonically valid temporal paths persist, producing a dynamic attractor stabilizing time's flow. Together, the coupled system UXT equals spacetime XT forms a unified, dynamic, resonant spacetime ocean governing spatial structure, causal flow, and event unfolding. The eigenmode decomposition of each field into spatial and temporal eigenfunctions with corresponding eigenfrequencies provides a detailed description of natural vibration patterns and stability conditions. Stability requires phase locking and modulation coherence across spatial, temporal, and modulation dimensions, ensuring deterministic evolution. The paper then applies this framework to planetary systems. explaining how planets actively modulate the surrounding spacetime ocean rather than simply contributing mass. A planet's rotational dynamics, orbital motion, internal energy distribution, and structural coherence inject characteristic oscillatory modulation patterns into the spacetime field. The local spacetime field near a planet is modeled as a baseline field plus a modulation-induced adjustment, characterized by sinusoidal spatial and temporal components, attenuated exponentially with distance. These modulations induce specific pressure gradients in the spacetime ocean, which manifest as gravitational attraction. Mathematically, the gravitational pressure gradient, PR, is given by the negative spatial gradient of the planet-modulated field. Upon averaging over rapid oscillations, this gradient reduces to an expression matching the classical inverse square law of gravity, corrected by AMC coupling factors. This shows that the classical gravitational acceleration emerges naturally from modulation gradients, explaining the scaling of gravity with mass, the formation of potential wells, and the stability of orbits as modulation attractors. To validate the model, the paper reproduces Earth's gravitational acceleration exactly by calculating the energy density UG from the modulation field's elasticity energy, incorporating geometric correction factors beta and gamma. The elasticity energy depends on the planet's orbital velocity, rotational period, surface area, volume, and a geometric correction davda. These correction factors are not arbitrary, but emerge directly from the mathematical structure of the modulation field through higher harmonic terms. For Earth, using known physical parameters, the calculated gravitational acceleration matches the standard value of approximately 9.8 meters per second squared. A crucial aspect of the framework is the role of the auxiliary modulation coordinate, EP. The AMC dimension is not a conventional spatial dimension, but a modulation dimension that organizes oscillatory patterns coherently. The modulation field equation includes second derivatives with respect to creating resonance patterns and standing waves in the AMC dimension. Coupling terms between AMC and conventional spacetime dimensions allow energy exchange, which manifests as spacetime elasticity. When spacetime deforms, energy flows into AMC resonance patterns. When deformation relaxes, energy flows back, producing restoring forces. This energy exchange underpins the observed elasticity of spacetime, linking the AMC field structure directly to gravitational phenomena. The paper further outlines how pressure gradients in the modulation field causally produce energy density, which corresponds to the elasticity energy observed in gravitational field measurements. This causal chain is articulated through explicit mathematical steps from the modulation field equation, through pressure gradient calculation, to energy density integration, and finally to gravitational acceleration determination. Beyond reproducing classical gravitational results, the AMC framework predicts fine structure in gravitational fields stemming from higher-order AMC resonance modes. These harmonic correction series introduce subtle oscillatory variations in gravitational strength, which could be detected with sufficiently precise measurements. The paper provides weighted contributions from the first 5 harmonic modes, showing how these create measurable fine structure patterns in the gravitational field. The AMC coupling also modifies orbital dynamics by introducing corrections to classical Keplerian elements such as semi-major axis, eccentricity, and inclination. These corrections depend on the AMC resonance structure and produce specific phase-dependent deviations from classical predictions. High-precision satellite tracking could detect these anomalies, providing empirical tests of the spacetime ocean model. Several experimental predictions arise from the framework. Resonant distance effects imply that gravitational strength should show subtle enhancements or reductions at specific radii related to the AMC wavelength. Temporal modulation introduces phase-dependent fluctuations in gravitational strength correlated with planetary rotation periods, with amplitudes potentially detectable at the parts per billion level. Gravitational wave propagation is predicted to exhibit dispersion effects depending on frequency, deviating slightly from general relativity's predictions, which could be tested with future gravitational wave observatories. To validate these predictions, the paper proposes multiple experimental approaches: high-precision satellite gravimetry to detect spatial resonance patterns, lunar laser ranging to observe temporal phase-dependent variations, gravitational wave detectors tuned to frequency-dependent dispersion, and deep space probes measuring gravitational fine structure at resonant distances. Successful detection of these signatures would provide strong empirical support for the modulation-based spacetime ocean model. The framework also addresses the quantum gravitational interface. It predicts coupling effects where quantum coherence influences gravitational dynamics and vice versa. Highly coherent quantum systems should produce measurable gravitational anomalies. In regions with extreme spacetime modulation, such as near black holes, should reveal unique quantum signatures not accounted for in conventional quantum field theory. These interface effects offer a pathway to unifying quantum mechanics and gravity. Philosophically, the spacetime ocean model shifts the perspective on reality by emphasizing the primacy of modulation patterns over fundamental substances or particles. Quantum phenomena emerge deterministically from modulation attractors rather than intrinsic randomness. The model unifies space, time, gravity, and quantum effects as aspects of a single underlying modulated field. Observers are incorporated as specific modulation patterns within the spacetime ocean, participating in the system rather than existing externally. Measurement processes correspond to natural modulation couplings, and conscious awareness may represent a resonant modulation class, aligning with Wheeler's participatory universe concept, but grounded in precise mathematics. The paper suggests several future research directions. These include pursuing quantum gravity unification via the modulation framework, exploring cosmological implications such as dark energy and dark matter as large-scale modulation patterns, connecting the entropy-resolved resonance selection mechanism to information theory, and investigating complexity and emergence within this unified physical framework. In conclusion, the paper presents a comprehensive, mathematically rigorous model of spacetime as a dynamic, oscillatory ocean. Gravitational phenomena emerge as pressure gradients within this modulated field, reproducing classical gravity measurements exactly while providing new insights into the quantum gravitational connection. The auxiliary modulation coordinate plays a central role in generating spacetime elasticity and deterministic quantum behavior. The framework makes specific, testable predictions that differ from conventional theories and suggests novel experimental pathways. By shifting from a static geometric to a dynamic oceanographic perspective, the model offers both intuitive understanding and powerful mathematical tools for probing the fundamental nature of reality. Beneath the apparent solidity of the universe lies a rich, flowing ocean of modulated structure whose waves and currents manifest as the forces and particles we observe. This unified view invites a profound reimagining of our relationship with the cosmos, as modulation patterns dancing within an active responsive medium rather than as objects moving through a passive background.